So good morning, everybody. Thanks for the opportunity to speak at this event. So I'm going to present our work from the University of Glasgow in the Glasgow Computational Engineering Centre on brittle crack propagation. And it's part of an ongoing programme of work that we have with EDF Energy. And therefore it has a nuclear engineering context. And it's also part of my Royal Academy of Engineering research chair. So just very quickly, the motivation for this particular piece of work is the nuclear industry. The majority of the UK's nuclear power, which provides about 20% of the UK's electricity, comes from 7 nuclear power stations with dual advanced gas-cooled reactors. And they were designed in the 60s and built during the 70s, and they are getting to the end of life. The reactor core of each of the reactors is comprised of graphite bricks, and these graphite bricks are stacked on top of each other to create the fuel channels into which the nuclear fuel is placed. Each of these bricks is about 1 meter tall and about 450 millimeters outer diameter. They're cylindrical hollow sections, and the graphite reactor core acts as a neutron moderator, so it controls the nuclear reaction. It provides mechanical stability and it provides thermal inertia. And it is probably the single most important life-limiting component of the nuclear power station. So once safety or integrity is compromised within these reactors, it cannot be replaced. And so that ultimately then deems end of life. If you look a little bit more closely at a typical graphite brick, you can see it's quite a strange geometry. And during the many years of operation as subject to radiation damage, then there's significant weight loss, loss of strength, loss of stiffness. But also early in life, the individual bricks are subjected to a complex stress state where the outside is in compression and the inside is in tension. But due to aging, at some point during their life, there's a stress reversal process such that the outside of the graphite bricks become tensile. And of course, what you'll notice is that we have these keyways around the outside of the individual bricks, which are there to allow interconnection of the bricks in the reactor. But they also act as fantastic stress raisers in a situation where the brick is experiencing tensile stresses on the outside. If you look at routine inspections down a particular, look down through the fuel channels into the inside of these graphite bricks, you can see crack patterns that have been observed. So on the left are so-called bore cracks, and on the right are so-called keyway root cracks. And these have been observed over the last few years in some of the older power stations. So that's the context. So we have been working on developing a modeling framework for modeling the unstable brittle crack propagation in these graphite bricks. A formulation that's based on global changes of energy with the minimum number of material parameters. In fact, the only material parameters we use for quasi-static analysis is Young's modulus, Poisson's ratio, and fracture energy. We are modeling the crack as a discrete displacement discontinuity within the context of finite elements, as you can see on the picture on the right. And we're recognizing that there are many other approaches, and we'll see some of those a bit later on, different approaches. But in our approach, we are modeling the crack as a discrete displacement discontinuity. So we've got complex crack paths in complex three-dimensional bodies that are themselves subjected to quite an extreme environment. Perhaps most critically, but one of the biggest challenges we faced, is that the cracks that we have observed are largely driven by the complex internal stress state, not just by any external loads that are applied. So it is the changing internal stress state combined with the changing material properties that is thought to be the cause of these cracks. And the additional complexity we have is that we also have contact between interacting bricks, and that's another issue that I'll hopefully get a chance to briefly talk about. So the modeling framework is provided through configurational mechanics, which in itself is not a new idea, it dates back to Eshelby, but it is with modern finite element technology that we're really able to exploit this now. We've extended the formulation, our original formulation, to capture the effect of internal stresses, contact, and material heterogeneity. And all of this is solved using the finite element method. But typically, most commercial software will not be able to tackle the sorts of problems we're dealing with. You need really research code, which is using the very latest advancement in finite element technology to be able to give you, enable you to model the types of problems we're interested in. So configurational mechanics in a nutshell is, well, if we take a body subjected to load, what we observe is elastic deformation and a crack propagation. What configurational mechanics allows us to do is to decompose the problem into a crack extension and the elastic deformation. So we decompose the problems into these two cases, whereby all the energy dissipation is only due to the creation of new crack surfaces. So we're dealing purely with linear elastic brittle fracture. Without going into a huge amount of detail around the formulation, what we've done is exploited the local form of the first law of thermodynamics to provide us with an expression for equilibrium of the crack front. And that's given by this equation here. And very briefly, G is the so-called configurational force, sometimes called the material force. And it is essentially the integral of the Eshelby stress around the crack front. And the resistance to that configurational force is the material resistance, which is given by the fracture energy and this kinematic variable A, which describes the crack front orientation. So this gives us an expression for equilibrium of the crack front. We also exploit the second law of thermodynamics, which defines the crack evolution. And all of this is supplemented then by a criterion for crack growth based on Griffith's criterion. So that's basically the essential framework. And then just very briefly show you how that works in practice. Here we've taken a simply a 3-point bending test on a simply supported beam with an initial notch. And then what we're doing is just advancing the analysis. So the green arrows here are the so-called configurational forces. They are driving the crack propagation. The blue line is the crack front and the red is the crack surfaces. It's important to say here that we are solving simultaneously for the equation of linear momentum balance and the crack front equilibrium equation at the same time. So there is no post-processing going on here. The green arrows, these configurational forces, are a natural consequence of our analysis. So what we end up with is a continuous and implicit advancement of the crack front, continuously re-establishing crack front equilibrium as well as elastic equilibrium as well. So you can see here that the crack propagates, it negotiates the free boundary and carries on propagating. So you can see it then, when you animate it, you get a very smooth, continuous advancement of the crack front. There's a whole load of other technology that we've introduced, a mesh cutting algorithm, continuous smoothing of the finite element mesh, as well as having to trace the nonlinear dissipative load path using an arc length control method. So because it's an unstable, highly nonlinear problem that we're trying to simulate. Okay, we've validated it against a whole range of experimental problems. The first two here I'm showing you are actually experiments on graphite, but on virgin graphite. And of course, that's one of the problems. You can't do experiments on irradiated graphite. And then the third example here is just in plexiglass, another brittle material. But the formulation that we've developed, whether it be in essentially what are planar problems or in complex three-dimensional problems, it performs extremely well. Okay, so that's just that's the introduction. But the real challenge has been in extending the formulation to drive the crack propagation by internal stresses. So what we've done is we have to first of all simulate the aging process, and so capture the effect of radiation on the development of internal stresses and material properties. And then we map those onto a finite element mesh of the brick that allows us to then do a crack propagation analysis. Now, that requires an extension to the mathematical framework. So normally when we're doing an analysis where we have external loading, we're trying to simultaneously solve the linear momentum balance equation and the material counterpart. So we end up with two expressions for equilibrium that we're trying to solve simultaneously. But when we are, and the term lambda here is our so-called load factor, so we can then scale the external load in order to drive the crack propagation. But when the problem is driven by internal stresses, then we have to change the equations that we are solving, and we have to, and we're now scaling the internal stresses in order to drive the crack propagation. And so we end up with a different system of equations that we're trying to solve. And as you can see, the additional terms that come from that are fairly complicated. So let me just show you an example of this in practice. Here's a graphite brick. You can see it's a complicated geometry. We've removed rigid body motion. We've seeded a crack. We've got a crack initiation at the corner of the so-called keyway root. And that's where we think that the crack is most likely to be initiated. So we always initiate the crack. Okay, so there's no crack initiation component in this. We initiate a crack, and then we run the analysis. So this animation is showing the crack propagating along the length of the brick as a result of scaling the internal stresses. So on the top left, you can see an animation of the crack propagating. You can see the green arrows are the configurational forces that are the driver for crack propagation. You can see it negotiating this complicated change in geometry. On the top right-hand side is the outside view. And on the bottom left, I'm plotting the load factor on the vertical axis versus the crack area on the horizontal axis. So what we're saying is, how do we have to what extent do we have to scale the load factor in order to get this crack to propagate? So if it's above 1, we have to scale the internal stresses greater than the stresses predicted as a result of aging. If it was less than 1, then we'd be predicting that cracking would have already happened at that age or that dose of irradiation. And you can also see that there's a slight spike in that graph, and that's where the crack is propagating along the brick and is negotiating this change in geometry, which acts as maybe not a crack arrestor, but it certainly inhibits the crack propagation. So that's a keyway, so-called keyway root crack, which matches very closely to what is seen in experiments. And another example here is where we have a so-called bore crack, where the crack is seated on the internal surface of the brick. Again, rigid body motion is removed, and we then run an analysis due to the internal stress state that is predicted as a result of aging. And you can see here the crack propagates in a kind of circumferential manner. This is a very difficult analysis because you've got a very, very long crack front with lots of parts interacting with the free surface of the brick. So you see the crack continuously propagating in a circumferential direction around the brick. And if we look at some snapshots of that and compare it to what's observed during inspections, on the bottom left is the images from the inspection, and then on the right are our simulations at different snapshots in time. And qualitatively, we're getting pretty good agreement with what's observed in reality. Okay, so that's the influence of internal stresses, but we then came across another big problem, and that was where we have contact. So essentially, we've got a problem where we have got two interacting parts, and the crack front crosses the contact surface that is under pressure. Okay, so where you see that crack contact interface, the challenge is where you have a crack that is passing across that interface. And you have a strong interplay between the contact forces and the crack evolution. And that required, again, some extension to our formulation to capture this complex scenario. So in this particular example, we are top and bottom of the sample are being pulled apart after a crack is initiated, and laterally it's being compressed by these by external pressure.
Please, 1 minute, please.
Okay. So as you can see here, the crack nicely is able to negotiate that contact surface. And you can see the interplay between the contact surface and the crack propagation. So the real problem we're trying to solve is an experimental setup to predict what's happened in the reactor, because in some of the reactors you have bricks that have a seal between the bricks, and therefore you've got this complex contact as well as crack propagation. So we've got a situation where we've got some contact with initial gap and some contact with no initial gap. And this final animation, I'll stop after this, just shows you our predictions of the crack propagating. The red surfaces are the contact surfaces, and you can see the analysis. It's struggling a little bit, but it makes it through and goes through that contact surface. And as a result of that, you end up with this fragment that we're predicting. This is an experimental problem. This is not a real problem. This is an experimental setup. And on the right-hand side is the experimental fragment. On the left-hand side is the result of our simulation. And again, qualitatively, we're getting pretty good agreement, given the complexity of the problem. Okay, I was going to show you very briefly material heterogeneity, but I'll skip it because just in the interests of time. So, in summary, we've used configurational mechanics as a framework for crack propagation. We have continuous and robust resolution of the crack surface evolution and advancement of the crack front, resolved within the context of the finite element method. The real challenge for us has been not to drive the crack through external loads, but to drive the crack propagation as a result of complex internal stresses. And the other big challenge we then faced is the interplay between contacting components and a propagating crack. We've also briefly looked at material heterogeneity, and actually for the main problems that we're dealing with the graphite bricks, we found that material heterogeneity, although it exists, doesn't have a huge effect on the crack path. But we've shown with other problems, obviously, that material spatial variation of Young's modulus, for example, can have a big impact on the crack path, depending on the severity of the spatial gradient. All of this is implemented into an open source finite element code called MoFem, which can be freely downloaded, and we'll be happy to talk to anybody who's interested in using it. And thanks to the Royal Academy of Engineering and EDF Energy. And I'll stop there. So thank you very much.
Thank you, Chris. So actually we are running out of the time. So any question? Yeah, Kevin, please.
Yeah, thank you very much, Chris. A great exposition of that. But when you look at the design of this bit of graphite, a very brittle material, you can imagine making a piece of glass with those sharp corners. The designer really got it slightly wrong, didn't he? Why don't you make a keyway which has got a more rounded design to it?
Well, I mean, I think the reality is they didn't expect this stress reversal to occur. So when they designed it, they assumed it was going to be in compression on the outside, and they didn't predict the effect of irradiation damage and creep and all the other things that have happened, and that has led to this stress reversal. So it was simply, I think, as my understanding is, they just didn't predict it. But the consequences are significant.
Yeah, it is. It is a very complex problem, isn't it? And I guess also using your method, you've calibrated that with the sort of simpler geometries you looked at earlier and you showed in your earlier slides. And do you get the nice fits then? We have those simpler, more understandable geometries. You find that you're getting a good fit to your theory with those.
Yeah. So, exactly. We get for genuine linear elastic problems, we get a very good result compared to the both the kind of theoretical and experimental results. We can recreate the stress intensity factors very accurately. So yeah.
Thank you.
Okay, thank you. Two short questions, more and nothing else. So please, Professor Banks, your question.
You're muted.
You unmute, please. You are mute.
Sorry. Leslie, that was a really interesting talk. I enjoyed all your graphics to see how the cracks propagated in a three-dimensional sense. Just from an engineering point of view, can't the United Kingdom replace all of those, you call them bricks, those, they look like pipes to me. Can't they be all replaced and maybe designed a little differently so that you don't have that keyhole?
No. The reactor is not replaceable in this particular design. So we are embarking in the UK. We're building a new nuclear power station at the moment, and potentially plans to build future ones. But these old ones will probably quite soon start being decommissioned.
Okay, thank you.
Thank you. And the last question, Siva, please.
Hi, Chris Pearce. It was very interesting talk on the final element modeling. Just the questions on the effect of actual experimental situation, the graphite as a radiation, heat, other particles might have some certain crack propagation started. Have anything addressed on that? And also, you know, the heat transfer point of view, certain synthetic graphites can be treated, for example, even highly thermal conductive materials, for example, has been thought about on any surface treatment on that.
Well, of course, in the actual reactor, I mean, this is an extremely aggressive environment, and all they have inspection channels, and all they can do is look into a few inspection channels on a periodic basis. But you can't go in and do anything, as I understand it, to the reactor as a whole. It's because of the obvious environment.
Obvious.
Hello, I'm not sure that I'm using Zoom properly. I'm not well acquainted with Zoom.
Sorry, we are running out the time. So
it is a very important question. I believe it would be beneficial to everybody. First, I would like to be sure that I understood what was presented in the configurational approach shown. Am I right that you are saying that you are including configurational forces within balance loads?
So I didn't catch the last bit.
That you are including configurational forces that are driving crack propagation into balance loads.
Sorry,
into conservation of momentum, yes. Linear momentum.
Yeah, so we have.
So how do you justify that?
Because we justify, it's a decomposition. So we're solving linear momentum balance in the classical sense, but we also have an additional material counterpart, if you like, of solving that momentum balance in the material configuration. So you're not adding configurational forces into the linear momentum balance equation. You're solving two dual problems, which are coupled.